breaking developments in the world of astronomy, as the Virtual Telescope Project has officially released new high-resolution images of the interstellar object known as 3I's ATLAS. This object, traveling from deep beyond our solar system, continues to draw global scientific attention due to its mysterious origin and unusual trajectory. The latest images capture its structure with striking clarity, giving researchers a rare opportunity to study a visitor that did not originate from within our planetary neighborhood. These new visuals reveal a faint, elongated body surrounded by a thin, glowing halo, indicating possible material trailing from it. Experts note that its composition appears unlike typical comets or asteroids seen in our solar system. Observatories around the world are now refocusing their instruments to collect further data, working to determine what this object is made of and how long it may remain visible. The movement of 3I's ATLAS is also raising new questions about how many such interstellar objects may be passing through unnoticed. Scientists suggest that this may not be a rare event, but rather one that we have only recently gained the tools to detect. With each new observation, our understanding of the wider galaxy deepens, and this object becomes a symbol of how much remains undiscovered beyond our sun's gravitational reach. The Virtual Telescope Project's contribution marks a significant moment in ongoing research. The astronomical community now moves forward with renewed interest and urgency, eager to unlock whatever secrets 3I's ATLAS holds as it continues its silent journey across the stars. The new images released by the Virtual Telescope Project offer a clearer and more detailed look at the interstellar object 3I's ATLAS, giving astronomers the opportunity to observe its structure and material characteristics at a level of precision that was previously not possible. These visuals show the object in a sharp, high-resolution format, allowing experts to identify the shape, brightness patterns, and possible variations in surface composition. The object appears elongated, with a faint, hazy glow trailing behind it, which could indicate that it is shedding material as it moves through space. This trailing effect suggests that 3I's ATLAS may possess volatile components similar to comets, yet its behavior and structure do not completely match the features of comets typically found in our solar system. Its surface texture and reflective properties seem unfamiliar, signaling the possibility of elements or compounds formed in environments outside those that shaped objects within our own planetary system. For researchers, the most striking element in these new images is the unusual reflectivity of the object's surface. Some sections appear brighter than expected, while others remain dull and shadowed, implying variations in density or composition. This uneven reflectivity could be a sign of fragmentation, layering, or a combination of icy and rocky materials that have undergone different phases of heating and cooling during its long journey across interstellar space. The thin halo surrounding 3I's ATLAS could be composed of dust or gas being released as the object reacts to the sun's energy while moving closer to our solar system's inner regions. However, the rate at which this material is released seems slower and more gradual compared to many known comets, adding to the mystery and prompting scientists to reconsider classifications that were once thought to be clear. The shape of the object has also captured attention. Instead of being round or loosely spherical, 3I's ATLAS appears to have an elongated, stretched form, similar to other interstellar visitors previously recorded. This shape supports the idea that objects traveling between star systems may experience extreme rotational and gravitational forces reshaping them over time. Unlike objects shaped within the gravitational influence of a single star, interstellar bodies may have been exposed to collisions, cosmic radiation, and temperature extremes that leave lasting imprints on their physical form. The new images display the object rotating slowly, giving astronomers the ability to observe multiple angles and confirm that this elongation is not simply an illusion created by camera perspective. Another key detail provided by these images is the subtle variation in the tail or coma region surrounding the object. The glow is faint and less dense than what is typically associated with active comets. This suggests that 3I-TLS might be carrying rare or unstable compounds that release energy differently when exposed to heat. It could also mean that the object is older than many known comets, its volatile materials already largely depleted during past interactions with stars. If so, what remains of 3I's ATLS today may be the hardened core of an object that originated in circumstances drastically different from anything found inside our solar system. The significance of being able to observe these details cannot be overstated. Every interstellar object that passes through our region of space is a messenger from a distant environment. The materials that form such objects hold clues about the history of planetary systems beyond our own. The fact that 3I-TLS appears structurally and compositionally different further reinforces the idea that planetary systems across the galaxy develop under diverse conditions. The chemical fingerprints of this object may reveal whether it formed near a young star, a dying star, or within a region of intense cosmic turbulence. By carefully analyzing the light reflected from the object, scientists can estimate temperature, mineral content, and even whether organic molecules might be present. Such discoveries could inform research into how life-supporting materials spread through the galaxy. The release of these images marks a significant advancement in observational capability. Capturing detailed visuals of a fast-moving, dim interstellar object requires precise timing, powerful adaptive optics, and advanced image processing. The success of this effort demonstrates how far technology has progressed and how collaboration within the scientific community is enabling deeper exploration of cosmic phenomena. The images also provide a foundation for continued monitoring as the object moves further along its trajectory. Future observations may reveal changes in its surface or tail emissions, helping researchers learn how interstellar objects respond to solar energy over time. As astronomers analyze these images in greater detail, the mystery of 3I-TLS becomes not just an isolated event, but part of a growing pattern that is reshaping our understanding of the universe and the unseen travelers that move silently between the stars. The latest observations of 3I-TLS are encouraging scientists to consider that visitors may be far more common than previously believed, and that their detection is increasing due to improved observation technology rather than any sudden rise in their presence. In the past, objects traveling from beyond the solar system would have passed unnoticed because the tools used to track faint, fast-moving bodies were limited in resolution, sensitivity, and detection range. Now, with automated sky surveys, advanced telescopes, and real-time global monitoring networks, researchers are recognizing that our solar system is not isolated. Instead, it is part of a much larger cosmic environment where material and objects drift across interstellar space, shaped by forces and conditions that differ greatly from those near the sun. The discovery and imaging of interstellar objects like 3I-TLS suggests that our galaxy may be filled with fragmented planetary remnants, rocky cores, icy debris, and other types of cosmic matter traveling across immense distances. These objects may have been ejected from their original planetary systems due to gravitational disturbances, collisions, stellar explosions, or the natural evolution of stars. If this is the case, then each object represents a physical record of the conditions that existed around another star, offering clues about how planetary systems form, change, and sometimes break apart. The presence of 3I-TLS reinforces the idea that planetary development and destruction are not uncommon events, and that material from these events can travel across the galaxy for millions or even billions of years before entering our region of space. The improved detectability of objects like 3I-TLS is a direct result of advancements in space surveillance technology. Modern observatories now employ automated tracking systems capable of detecting dim light sources moving against the background of distant stars. Artificial intelligence and optical filtering techniques help distinguish between ordinary near-Earth objects and those with unusual trajectories. These systems analyze motion patterns, reflectivity, and orbital paths to quickly identify objects that do not originate from within the solar system. The Virtual Telescope Project's ability to capture high-quality images of 3I Gatalas despite its faint brightness shows how far observational astronomy has progressed in just a few years. Instruments that once struggled to detect nearby asteroids can now reveal details of objects that have crossed light years of space before reaching our view. The growing number of interstellar detections is also reshaping scientific theories about how materials move between star systems. If objects like 3I ATLAS are indeed common, it suggests that the boundaries between planetary systems are more porous than previously assumed. Instead of planets and their debris remaining confined to the areas around their host stars, violent events such as orbital shifts or close stellar encounters can propel fragments outward into interstellar space. Over time, these fragments drift along gravitational currents created by stars and galactic forces. The movement of such material could contribute to the distribution of chemical elements across the galaxy. This means that some of the building blocks of Earth and our solar system may have originated from distant stars, transported long before the sun and planets formed. The continued observation of 3I ATLAS also has implications for future research missions. If these objects are more common than once thought, it may be possible to plan targeted missions to study an interstellar object up close. Such a mission would allow researchers to directly analyze surface materials, internal composition, and structural properties. For now, scientists rely on light analysis and remote imaging to interpret characteristics. However, the idea of sending a probe to intercept an interstellar object is no longer considered impossible. With improvements in early detection, trajectory prediction, and propulsion systems, the prospect of studying such an object in situ becomes more realistic. The scientific value of such a mission would be immense, offering data that cannot be obtained from remote observation alone. At the same time, the detection of interstellar objects encourages new perspectives about the nature of our own solar system. It presents the possibility that objects from other systems may have entered here in the past, leaving behind material that eventually integrated into asteroids, planetary surfaces, or even the early Earth. If this is true, the origins of some elements or organic compounds found within Earth's geology and atmosphere may have been influenced by interstellar transfer. Such a concept supports theories about panspermia and the distribution of life, supporting chemical ingredients throughout the galaxy. The ongoing study of 3I ATLAS may contribute to determining whether such exchanges are plausible, raising questions not only about where matter travels, but also how the potential for life may spread across star systems through natural cosmic processes